Okay, good day everyone, and thank you for the introduction. So part of this work I did while I was still a postdoc at KU Leuven in Belgium, but yeah, now I'm doing a postdoc at NYU Abu Dhabi, quite close by. So what will my presentation be about? Well, as the name implies, we're going to attack routers, and we're going to use symbolic execution. So to start the presentation, I'll first give a high-level overview of what symbolic execution is and how it works. And then we're going to extend it so we can symbolically analyze cryptographic protocols. So we're going to extend it so we can handle cryptographic primitives. And why are we going to do this? Well, because we can then apply symbolic execution to the four-way handshake of Wi-Fi. So I'm still attacking Wi-Fi. I like attacking Wi-Fi. And we found some vulnerabilities using this technique. Now, some of these vulnerabilities are more on the theoretic side, and some have quite some preconditions. So I would not say that the takeaway of this talk is that we found cool new vulnerabilities. It's mainly that we have a new technique to discover them, and that's the main interesting part of the work that we did. But at the end, we'll go over some of the results, and we will explain how we can exploit some of these vulnerabilities to, for example, gain code execution on a router. So let's get started with the first part, symbolic execution. And let me introduce it immediately by starting with a very concrete example. Our goal is to apply symbolic execution to network code. So let's start with this simple example. It's a function that receives a network packet, and in this case, it will first validate if the header of the packet is valid, and then it will do some kind of calculations based on the content of the packet. So here we can see it accepts data as the parameter, which will contain the payload of the packet, the content. It has a certain length, and in the first if test, we check if the first byte equals 1. You can imagine in the protocol, it will check the version number that is included in the header. And if this version is incorrect, it will simply drop the packet. On the other hand, it will also check the second byte. It has to be equal to the length of the packet. And if not, the packet will again simply be dropped. And if then the header is valid, it will perform some kind of calculation on the content of the packet. And we now want to fuzz or analyze code like this in order to discover vulnerabilities in it. Now, if we would apply traditional fuzzing here, where we simply generate random values, it can be a bit tricky to pass these kinds of conditions, because we need to randomly hit these two conditions at the same time, and this will slow down if we use traditional fuzzing. It will require a lot of time before we hit exactly those requirements. And this is where symbolic execution comes into play. Symbolic execution is a technique to explore all the paths that your code can possibly execute. And how does that work in practice? Well, in practice, we would mark our data as symbolic, and then we would analyze the function as if it is executing on this symbolic data. So that doesn't mean we can run a program as normal anymore. We can't just compile it with GCC and run it. We need a special kind of symbolic execution engine. And the main difference with a normal execution of a program is if we now hit an if condition, if we hit a branch that is based on a symbolic variable. For example, if we look here at the first if condition, since we marked our data variable as symbolic, now the program would be checking, is this symbolic byte equal to 1 or not? And just to recap, a symbolic variable means that we assume it can take on any valid value. And here we are asking if it equals a certain value or not. And to handle this, we are essentially going to fork the execution of this program into both cases. So we're going to fork it in the first case, and we are going to assume that this first byte doesn't equal 1, and in this case, the program would then execute the return function, and it would stop executing. And then we also have the other condition, namely, if this first byte does equal 1, and in that case, we're going to continue with analyzing the function. So another way to explain this is if we symbolically execute a program, we first start with one instance of the execution, and whenever we hit a branch that is based on a symbolic value, we branch into the two possible cases. We branch where the if condition is true and where the if condition is false. And that way, we will be able to explore all possible paths that a program will take. And when we are analyzing the program in this way, we will also keep track of all the conditions that must hold in order for a program to follow a certain execution. So what do I mean with that? If I encounter an if test, I assume this if test will be true, I will record the condition that must hold in order for the program to actually take that if test. And these conditions are called the path constraint. So these are the conditions that the input must adhere to in order for the program to indeed execute along this way. So as I mentioned, in the first case, the function would immediately return. And in the second case, we would continue analyzing our program, and we would then hit the second if condition in our program. And this is again a branch based on symbolic input. So we again fork the execution, and we add both conditions to the path constraint. And then we continue analyzing these paths as well. Here in the middle case, we would again immediately hit a return value, and we would return. We would stop analyzing the function. And in the other case, we would continue analyzing our receive function. So you can see here, with this technique, we really can explore all paths of an execution, because whenever there's a choice about which code to execute, it will fork to explore all possible paths. Now, let's get back to our example. Assuming that these two if conditions are not true, we would end up at the code below, where we divide the length by the third byte in the packet. And in this case, we have a division, and we know if we divide by 0, we have a problem. So the interesting thing with symbolic execution, we can now ask our symbolic execution engine, can this byte ever be equal to 0 under the current path constraint? So given the conditions that must be adhered to reach this code, is it possible that this third byte equals 0? We can ask that to our symbolic execution engine. In this case, the answer is yes. This byte can be 0, meaning we possibly have a vulnerability here. So this is a quick introduction to how symbolic execution works. In practice, there are some tools that already implement this, and in our case, we used CLI. The reason why is because this tool is actively maintained. It's fairly easy to change, and it works on LLVM bytecode. That means we can take a Java program, we can compile it to LLVM, and we can then symbolically execute it. We can also analyze C code. Anything you can compile to LLVM, this tool will support. Now, symbolic execution isn't a magic tool that will solve all your problems, obviously. It has some limitations. Namely, if you have a big program, it becomes infeasible to explore all paths in this program. There are just way too many. On top of that, it also cannot handle if you have an infinite loop in your program, for example, a while loop, or if you're processing linked lists, that can also pose a problem. And finally, another problem is something we call SMT query complexity. To explain that simply, remember in our example that we asked our symbolic execution engine a question like, can this certain condition hold? And asking these kinds of questions, they are answered by an SMT solver. And if your program is more complex, these questions will also become more complex, and it will take a very long time for your execution engine to answer and analyze these kinds of questions. Okay, so we now want to apply this technique to code that uses cryptographic primitives. Now, let's modify our example a bit so it actually uses encryption. In this case, we have our receive function again, and the first thing that it does, it will decrypt the data that it is receiving. If the decryption failed, it will simply exit and drop the packet. If not, it will process the remaining content of the packet. For example, in this case, I have an example where this packet might contain some kind of command that the receiver would execute. Now, let's say we would blindly apply our symbolic execution technique. So we would again mark the incoming data as being symbolic. The problem now is that our execution engine will also symbolically execute this decryption function. And this can be very time consuming for our symbolic execution engine to analyze. And to understand this intuitively, in a sense, our symbolic execution engine is summarizing what the decryption function is doing. And for some encryption algorithms, this can be summarized quite efficiently. But for other cryptographic protocols or cryptographic primitives, analyzing these implementations symbolically can take a lot of time. And it would really slow down our symbolic analysis. Now, let's just assume that in this case we are using some crypto where we can analyze this fairly fast. Then the second problem is if we then check whether the decrypted plaintext can equal a certain value. And to understand this intuitively, we're asking the symbolic execution engine to reason about our decryption function. And in a sense, crypto is made so it's hard to reason about, so it's hard to try to break it. Now, it's a bit of a simplification, but essentially, if we would symbolically execute this code, it would be time consuming, meaning we won't ever reach the interesting part of our program, where it's actually parsing our data. So now the question is, how can we solve this? How can we avoid that our decryption function introduces all this overhead? Well, it's actually really simple. One thing we can do is we can simply comment it out. And this would already work. So remember, if you ever have to do this yourself, this is a very quick fix. Simply replace the decrypt function by a stub function that is nothing, and then you already solve the big part of the problem. Now, in our case, we're going to do it a bit more complicated, but the idea is very similar to this. We're simply going to replace the output of the decrypt function with a fresh symbolic variable instead of summarizing this decrypt function. So if we go back to our example, we would now again mark data as symbolic, but instead of analyzing the decrypt function, we simply let this plain variable that represents the plain text be a fresh symbolic variable without any special conditions on it. And this will allow us to do a normal symbolic execution of the rest of the code. Now, why do we create this fresh variable instead of simply commenting out the decrypt function? The reason why is because we can then also check some more advanced properties, and I'll come back to that in a bit. But the takeaway message here is that by doing this, we can now actually analyze the interesting code of our protocol. And apart from handling decryption, we can also handle hash functions in a similar way. Instead of symbolically analyzing these hash functions, we simply replace their output by a fresh symbolic variable, and that's it. And one advantage of this approach is that we can essentially track the usage of crypto primitives throughout our code, and this will allow us to check more interesting properties. For example, one thing we can do is we can now also detect trivial side channel vulnerabilities. Imagine, for example, that you have a packet with a certain authenticity tag, for example, a signature or the output of a hash function, and then your implementation will compare if this output of the hash function equals the expected value. And if you want to do this securely, you should be using a constant time memory compare, which always compares all the bytes, and it shouldn't exit on the first byte difference, because otherwise you might have a timing leak. And by introducing our fresh symbolic variables, we can actually check if this is done properly. We can check that either no bytes of a hash output are in the path constraint, or whether all bytes of the hash input are in the path constraint. Because if there's only one byte in the path constraint, it means it does an early exit. So if this is not completely clear, just remember that we can detect timing side channels using this. Another thing that we can do with this technique is detect decryption oracles. Not going to go into too much detail here. Basically, what I mean with a decryption oracle is if your program decrypts data and then processes it without checking the authenticity of this data, then an attacker can potentially abuse this, because he can take an encrypted packet, he can manipulate it, and then forward it to the receiver, and the receiver won't detect that an adversary manipulated with the encrypted data. And in practice, this is something that an attacker can abuse to, for example, decrypt certain content. Okay, so this was a bit more on the technical side. But the idea is now to apply this to the four-way handshake of Wi-Fi, which is used in routers. So let me quickly introduce what the four-way handshake actually is. And whenever you connect to a protected Wi-Fi network, the four-way handshake is the thing that verifies that you possess the correct password of the network. In other words, it provides mutual authentication. The access point verifies that you know the password, and you verify that you are connecting to a legitimate network and that you're not connecting to the attacker, for example. And at the same time, this handshake also negotiates what we call the PTK, which is basically just a fresh session key which will be used to encrypt data after the handshake. Now, this handshake was originally part of WPA2, but I do quickly want to remark that even if in a few years you'll be using WPA3, or maybe this year already, then the four-way handshake is also used in WPA3. This is because in WPA3, we first execute what we call the dragonfly handshake, and after the dragonfly handshake, the four-way handshake is still being executed. So the takeaway message here, the four-way handshake is used both in WPA2 and WPA3. And to give a bit of a preview of the things we discovered some denial of service attacks against this handshake. We discovered a buffer overflow and also a decryption oracle. Now, some of these are more theoretic attacks, some of these are more practical, and we'll discuss that in a bit more detail later on in the talk. In order to properly understand these attacks, though, I want to quickly explain how the four-way handshake works at a high level. And to do that, I'm going to assume that we have our smartphone here on the left that connects to the access point on the right. And if you're connecting to an enterprise Wi-Fi network where you either authenticate using certificates or where you have a username or password, then first this optional handshake called 802.1x is executed, but we don't really care about this. The only thing we care about is that there is some shared secret between the client and the access point, and if that's the case, the four-way handshake can be executed. So how does this handshake work? Well, the first two messages of the handshake, they are used to transport a random number between both devices. So first, the access point sends the A nonce to the client, and here the A nonce is a random number, and A nonce stands for access point nonce. Once the client receives that, the client will generate its own random number called the S nonce, where S nonce stands for supplicant nonce, and supplicant is just a synonym for